Okay, good morning everybody. Just recording this prior to your lesson. Let's crack on. So this is nucleophilic substitution questions with a focus on nucleophilic substitution. So a nucleophile, I think the mark scheme says electron pair donor, but we're going to learn it as lone pair donor. Electron pair donor is fine, but a lone pair donor is how I'm teaching it to you. Substitution is this idea of replacement. One comes in and one goes out. So substitution as applied to nucleophilic substitution. So it's going to be the replacement of the halogen by the nucleophile. So to substitute means to replace. So it doesn't just mean remove. Replace, in this case, the halogen, replace a halogen with nucleophile. Bond enthalpy then. So this is from the other side. So it's the definition is the enthalpy change when 1 mole off. It's typically how we would do it. I'm looking at the mark scheme to the side of me and it doesn't go down that route, but the bond enthalpy, the actual definition is the enthalpy change when 1 mole of, because that's how all these enthalpy changes do. The enthalpy change when 1 mole of, in this case, carbon-halogen bonds are broken with everything in the gaseous phase. Sorry about straight in my writing, it's really spidery writing this morning. I'll try and slow it down. It's because I've got to get this done before taking the kids to school. Got about 20 minutes. Outline a mechanism for the nucleophilic substitution reaction in which 2-bromopropane reacts with potassium why is that really blurry? Has that been really blurry all the way, everyone? I'm so sorry if that's been the case. Outline a mechanism for the nucleophilic substitution reaction. Right, let's get this out of the way now. If it says potassium hydroxide, we're ignoring that. It's a spectator ion and they do it all the time, so we're just dealing with hydroxide ions. Outline a mechanism for the nucleophilic substitution reaction in which 2-bromopropane reacts with potassium hydroxide to form propan-2. Well, I would start by just drawing it. The reactants out here, 2-bromopropane. You get that mark, prop means 3. Reacts with hydroxide to form propan-2. Well, I'll draw the product down here. Propan-2-ol. And then you can just look at the reactants and the product and decide. It will make sure that you know what's going on. It's obvious to me that the Br has been replaced by the OH-. So I would put partial charges in, delta positive, delta negative. OH-, you've got to have a lone pair on it. Alright, OH- comes in and it goes to that carbon. This bond breaks onto the bromine. Plus Br-, I'm teaching you to put that lone pair in, although it doesn't get penalised if it's not there. Alright, 1 mark, 2 mark, and 3 marks, I imagine, for the products. Right, for mark 1, must show the arrow from the lone pair of electrons on the oxygen to the central carbon atom. Mark 2, must show the movement of a pair of electrons from the bond to the atom. Okay. Consider the following, sound a bit West Country there, Cornwally maybe. Consider the following reaction. Just pour me coffee. Little pleasures in life. Consider the following reaction. Here we go again, there's a little KOH, let's ignore the K, put an OH-, let's ignore the K and put a Br-. I imagine some of you were confused by the K. It really is coming in and out of focus today, isn't it? See if I can get that perfect. Maybe that's better. I don't know. Name and outline the mechanism for this reaction. Well, the OH- is obviously replacing, so that's substitution, it's replacing the Br. That's a nucleophile, so it's nucleophilic substitution. You have to write the words out. Mechanism. Literally exactly the same one as we've just done. Practice makes perfect. Right, if I was in the class, I'd be coming round and I'd be checking that this bond, this arrow is touching that bond, that this arrow starts at the lone pair and ends at the carbon. I would be checking for delta positive and delta negatives. Alright, you'd have to draw the product, including the Br minus. And you would have to put on the H's in these positions. Name the haloalkane in this reaction. The haloalkane is this one. Longest carbon chain, 3, so that's a propane. It's a propane because it's all single bonds. 2 bromopropane. Identify the characteristics of the haloalkane molecule that enable it to undergo this type of reaction. Well, it's got a polar CBr bond, but I would definitely put like that. I don't just want to say it's polar. I want to say how it's polar. Delta positive, delta negative. Compound A is a halogenoalkane. Yes, it is. Alkane, all single bonds. It's got a halogen there, chlorine. Name compound A. Longest carbon chain, 1, 2, 3, 4, 5. Yeah, it's 5. Pentane. I do this. Now, what else have I not named? I've named the pentane, but I've not named this methyl, and this chloro. So it's a dimethyl, and it's a chloro. Chloro is before chloro, dimethyl, K and D, alphabetical. Where is the chloro? It's in position 3, and the dimethyl is in position 2 and 4. 3 chloro, 2, 4 dimethyl pentane. Got to find my answers there. What question is this? Question 3. 3 chloro, 2, 4 dimethyl pentane. Alright. Compound A has a relative molecular mass of 134.5. The main isotope of hydrogen is H1. The main isotope of carbon is C12. Chlorine consists of 2 common isotopes, 35 and 37, of which 75% is chlorine 35. The mass spectrum of A was recorded when A was ionized by electron impact to form A+ ions. Draw on figure 1 the peaks for the main molecular ions in the mass spectrum of A. So A weighs 134.5 on average, the relative molecular mass, because that is 1, 2, 3, 4, 5, 6, 7 carbons, 7 times 12, plus all the hydrogens, plus the chlorine. When you do a mass spectrum though, you won't see a peak at 134.5. You will see a peak that corresponds to chlorine that weighs 35, and you will see another one that corresponds to chlorine weighing 37. That's what you'll see on the mass spectrum. So some of the molecules will have chlorine 35 in them, and some of the molecules will have chlorine 37 in them. Right? There is no molecule with a chlorine 35.5. Hope you realise that's nonsense. Chlorine only exists as 35 and 37. So the first thing to do is to work out where these peaks are going to be. So 35.5. So there's going to be one peak at 134. So just put a tiny little peak on there just to name it, and it's just to say where it is, and a peak at 136. Now, it says here that Chlorine 35 is 75% abundant, and this is 25% abundant. So it's 3 times more likely for a 3-chloro-2,4-dimethyl pentane to be in this form with a chlorine 35. So this will be 75%, and this will be 25%. So how do you show it on a graph with just lines? You show it like this, 3 to 1. So each of these could be 25, 50, 75, 100. If it was 100%, it'd be all the way here. So I can show this as 75% to 25%. Back to mechanisms. Reaction A with warm, dilute, aqueous sodium hydroxide. Remember what I was saying last time about that? Warm, dilute, aqueous. If you make it hot and ethanolic, you make a different product, right? You form alcohol B. Name the mechanism. So there are enough clues to tell you there's going to be nucleophilic substitution. Also, it's going to form an alcohol. Well, I can see already that the alcohol is going to be in this position. The OH minus is going to come in here. I'm telling you again, this sodium hydroxide, it's just hydroxide, so you're forgetting about the sodium, the potassium, or whatever else they put in to try and confuse you. Have you got that, everybody? Ignore the sodium, the potassium, or the spectator ion. It's a reaction with hydroxide. That's going to come in from there, and that's going to go onto there. Delta negative, delta positive. You could have drawn it from the bottom, you could have drawn the OH minus coming in here and the Cl minus kicking out, but this is how I'm doing it. Outline the mechanism using the structure, include the structure of the product alcohol B. 1, 2, 3, 4, 5. CH3, CH3, OH. They don't ask for displayed, so I'm just taking my lead of how they've displayed it here. Just checking everything, and then you've got to put the Cl minus as well. It gets kicked out. Look at the mark scheme, they haven't put the Cl minus that gets kicked out. They should have. Right, alcohol D reacts with dilute aqueous sodium hydroxide in a similar way to A. So it reacts with hydroxide ions in a similar way to A. Explain why D reacts more quickly than A. So I'm going to say display spot the difference. They're almost exactly the same, apart from this is bromine and this is chlorine. The CBr bond is weaker than the CCl bond. That's it. So as I say, so it breaks easier. Would probably be the best thing to write there. So there you go. That was that bit of knowledge that we came up with. Last time. Okay so far? Question 4, multi-choice. Which of these arrows labelled A, B or C is not correct? I'm happy with that. I'd rather they'd have gone all the way to the lone pair, but I'm happy with A. I'm happy with B. D is showing the ammonia picking off the hydrogen. This is the one that's wrong. C. This arrow is that one that feels squished in. C is the problem arrow there. No. Very common question. Which of the following statements explains why fluoroalkanes, so that's where you've got a CF bond, is the least reactive, and we've said before that this bond's really, really strong. D, which species could act as a nucleophile? Nucleophile, you need a lone pair because you are a lone pair donor. I'll go through these straight away. I know the answer is C. BH3, boron is in group 3. Alright, and if you've got 3 hydrogens, you haven't got a lone pair. NH4 plus, well that's NH3, but its lone pair is being taken up by a hydrogen, so ammonia doesn't have a lone pair. pH3, phosphorus is in group 5. 1, 2, 3, 4, 5, 3 hydrogens. It's got a lone pair. pH3 is just like NH3. Alright, P and N are in the same group. SiH4, silicon is group 4. It's just like CH4, that. Group 4, 4 electrons in the outer shell, 4 hydrogens, no lone pair. So only that one has got a lone pair. Question 7, pentane nitrile. 1, 2, 3, 4, and on the 5th one there's a triple bond N. Okay, we recognise this is one of the nucleophiles. Can be made from the reaction of 1-bromobutane. So you see, if you replace the Br with a Cn, that's what happens. With potassium cyanide, yeah, cyanide ion. See, ignore the potassium. Which of these is the correct name for the mechanism? Nucleophilic substitution. Why are fluoroalkanes unreactive? Where are you? CF bond is very strong. Halogenoalkanes are useful compounds in synthesis. A reaction pathway is shown below. So what you've got here is some sort of alcohol, but it's got a Br on the end. And then you look at the next one, and it looks exactly the same: CH2OH, CH, CH3, CH2. And instead of Br on the end, they've got an OH on the end. That is nucleophilic substitution. There's the sodium that they try and trick us with every time. Anyway, give the IUPAC name for this. I'll try it without drawing it out. I'm looking for carbons that are not in the bracket. So the main chain is 1, 2, 3. So we're dealing with a prop. It's an ol. It's got on methyl. Do you know what? I'm going to stick to my gun. I hate naming them from here. I'm going to draw it out. So you've got CH2 with an OH. That's a CH2 with an OH joined to it. So you read them from left to right. This OH is joined to this. This bracket is joined to this. Then you've got a CH with a CH3. So I've done this bit. And then you've got a CH2 with a Br. No apologies there. I find that really hard to read. So I've drawn it out in a way that I like to read it. So there's my prop. I've got an ol, a bromo, and a methyl. Well, so let's just have a little look then at how we might name this. So it's definitely a methyl. Bromo, it's definitely some sort of bromo, methyl, propan, ol. There's the bromo, methyl, and there's the ol. So the bromo is alphabetically in the front. The methyl is N, and then the ol is at the end. So the best way of doing this then, the priority group there will be the alcohol. The lowest priority will be the halogen. So you could name it 1 bromo, 2 methyl, propan, 3 ol, or you could name it 3 bromo, 2 methyl, propan, 1 ol, but the ol is higher priority to the bromo. So that is an example of where priority rules are important. And the priority rule we're using there is halogens take the lowest priority. It's 17 minutes in and I've got to take the kids to school. Arg! Reaction 1 occurs via a nucleophilic substitution reaction. What? Now we get it back. Yes, it does. Mentioned that before. Explain why the halogenoalkane is attacked by the nucleophile in this reaction. Oh, right. So I've got they're asking me about this. All right, this bond. All right then. So bromine is more electronegative than carbon. So that's a good start, I think. Therefore, the carbon will be slightly positively charged. Delta positive. Therefore, the OH minus will be attracted to it. The OH minus will be attracted to it. Therefore, the OH, the lone pair on the nucleophile will, we can call it attack the delta positive carbon. I like that phrase, will attack. It's called nucleophilic attack. It's a genuine thing, nucleophilic attack. The lone pair on the nucleophile will attack. What's the mark scheme say? I'm on the wrong page. Right, bromine is more electronegative than carbon. Cool, that's a good start. Carbon is partially positive. A lone or electron pair donates to the positive. Allow the lone pair is attracted to the positive. You've got to mention the lone pair. Okay, you've got to mention the lone pair. I'm glad I wrote that last sentence then. You've got to mention the lone pair. This can be awarded from a diagram. Oh, there you go. Well, if you're given all that space, yeah, you may as well draw it, I suppose. Little top tip there, which actually I'd forgotten about from last time I taught this. Even if they don't explicitly ask for the mechanism, you can draw a bit of the mechanism to try and explain what you're saying. Oh, 20 minutes. Oh, I've done that. Oh no. Question 10. 2-methylpropan-1-ol can be prepared by reacting. What time are we on? Sorry, let's go check the time. Got a couple of minutes. 2-methylpropan-1-ol can be prepared by reacting 1-bromo-2-methylpropane. Propane 3. 2-methyl CH3. Doesn't ask for displayed. 1-bromo Br. Delta positive, delta negative. Sodium hydroxide. You're not getting me. OH minus, lone pair, curly arrow from lone pair to carbon, curly arrow from there to there. Name and outline the mechanism. Nucleophilic substitution. 1, 2, 3. You're going to have an OH on there. The CH3 is on there. Bang, 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 bang. You need to draw these in. And then you're going to put plus Br minus, otherwise you don't get that mark. Oh, have I got time to do a calculation? No. I'm going to pause the video. You won't notice the pause, but I'm going to pause the video. Alright, they're just getting the shoes on, ready to go. So I'm just going to have a little look at this. When 2 centimeters cubed of this stuff with an MR of 1,3. Right, so what we know is that this stuff weighs 136.9 and we've got 2 centimeters cubed of it. They were reacted with an excess of sodium hydroxide, so you've got an excess of that. We're going to make 895, so that's 0.895 grams of this stuff, which has got an MR of 74. Were obtained. The density of this is 1.26 grams per centimetre cube. Notice I'm just putting everything where it's sensible to put it. Calculate the percentage yield for this reaction. So the percentage yield, you need to do 2 steps. You need to work out firstly what you should have made and then what you did make. So I've got the information here to work out what I did make. So this is going to be worth 1 mark. 0.895 divided by 74 equals, that's just mass divided by moles. I'm making 0.01209 moles. So there's a mark. Next part is to work out what I should have made, because this isn't what I should have made. I won't have made 100% yield. So I've got to turn 2 centimeters cubed of this. I've got 2 centimeters cubed and I know that it weighs 1.626 grams per centimeter cubed. I hope that's really obvious. If you've got 2 centimeters cubed of something that weighs 1.26 grams per centimeter cubed, if you go 2 times 1.26, 2 grams times 1.26 grams per centimetre cube, sorry, 2 centimetres cube, you'll end up with grams. That is 2.52 grams. You've got 2.52 grams of this stuff, and it's got an MR of 136.9. 2.52 divided by 136.9 equals 0.0184. 0.0184 moles. Alright, so you started off with 0.0184 moles. That means that you should have made, these react in a 1-to-1 ratio, you should have made 0.0184 moles of this. But you didn't, you only made this much. So your percentage yield is 0.01209 divided by 0.0184. 0.01209 divided by 0.0184 equals 65 times 100, 65.7%. Now I've done that really, really quickly, and yes, I've nailed it. 5, 6, 7, I got 10 out of 3. Alright everybody, I'm just going to upload that now, and I'll see you next time.